Welcome to the deep dive.
Glad to be here.
Today, we're navigating some fascinating structural chemistry.
Yes, focusing on something called the Chinese lantern coordination complex.
That name alone is intriguing, isn't it? It really suggests something quite specific visually.
It does. And our sources, well, they point towards how fundamental chemistry, especially involving metal acetates, creates these really quite beautiful architectures.
Okay, so our mission then.
It's really to understand let's say, the molecular foundation. We're distilling some pretty complex structural info, focusing on the star player here, the acetate ion, that's CH3CO2.
The acetate.
Exactly. We need to see how this small anion, this acetate, acts as the key molecular architect. It dictates the whole shape.
Right, so let's look at this architect then, the acetate group. What's it actually doing that lets it build these, elaborate cage-like lanterns?
Well, the key is its versatility. It has those two oxygen atoms.
Okay.
And acetate doesn't just stick to one metal ion. It cleverly uses its oxygens to bridge between two different metal ions.
Ah, linking them.
Precisely. That's what we call witty bonding, technically. Mu2.
Mu2 bonding, got it.
And it's this specific bridging mechanism, particularly when you get four acetates linking two metal centers along a central axis. Well, that's what wraps the metal core up like a cage.
Almost like the paper walls of the lantern.
That's exactly the idea,
Yeah.
hence the name Chinese lantern.
That really clarifies the structure. So if that bridging action is the key, where did chemists first really notice this specific kind of metal bridging?
That takes us back a bit to the molybdenum acetate dimer, Mo2O2CCH3.
Molybdenum acetate.
Yes, synthesized from molybdenum hexacarbonyl and just acetic acid. This structure has four acetates bridging two molybdenum atoms.
And there's a pretty remarkable historical lesson there, right?
Oh, absolutely. It is. You see, when this compound was first properly characterized back in 1960, researchers initially proposed a simpler tetrahedral shape.
They just assumed.
They assumed based on what was known then. They simply didn't realize yet that a quadruple metal bond was even possible.
A quadruple bond.
Exactly. The fact that these four bridging acetates actually stabilize this unprecedented bond, it completely changed how people viewed coordination chemistry. A real milestone.
That is a huge chemical milestone. Okay, so let's move from that foundational history to maybe more common metals, things with practical uses. What about copper-2 acetate? Our analysis touched on that.
Right, copper-2 acetate. Its full name is tetra-2-acetotioquatocopper, which tells you the structure right there.
Pretty mouthful.
It is. It's a dark green crystalline solid, and you'll know it if you see it on a flame test. It gives off this beautiful blue-green glow.
And its uses seem quite surprising.
They really are, quite varied. Historically, it was a base for pigments like the insecticide Paris green.
Insecticide, okay.
And get this, it was even deployed as a shark repellent during World War II.
Wait, a shark repellent? Seriously, how does that work? Is it the copper itself?
Well, the complex structure helps deliver the copper effectively, which is the active agent, yes. It's quite something.
Wow, okay. And we also see this stabilizing power with iron, right? Iron 3 acetate.
Exactly, often called basic iron acetate. The formula is Texto3 plus diphlera. That structure really highlights how acetate can bridge multiple metals simultaneously. See the F3, stabilizing these big trinuclear clusters.
And those iron compounds, they're still relevant.
Oh, yes. Our sources mention their practical use as dyes and mordants even today.
It's pretty amazing. That same tiny acetate ion helps anchor that foundational quadruple bond in molybdenum and also stabilizes these massive iron clusters used in, modern industry.
It's a testament to its versatility as a building block.
Well, this has been a fantastic exploration, really tracing how this humble acetate ion acts as a true molecular architect.
Golding everything from chemical history to modern materials.
Indeed. And this deep dive was sponsored by embersilk.com. If you're looking into AI, education, or integration, Embersilk is the answer for all your needs. Check them out at embersilk.com. And a quick reminder to you, our listeners, please subscribe if you haven't already, and maybe leave us a 5-star review. It genuinely helps us out a lot.
And just to leave you with a final thought, if acetate, which is a relatively simple building block, right?
Yeah.
If it can generate such structural complexity and utility, leading to things like quadruple bonds and even shark repellents.
Yeah.
Just imagine the potential if we start designing new complexes using the much more elaborate organic acids found widely in nature. Things like the quillic acid derivatives mentioned in some of the broader source material, the possibilities for new functional materials, well, they seem almost limitless.